Chapter 3 is symmetric ciphers. So these are real-world ciphers, symmetric ciphers that get used in practice. Now, as we mentioned, there's two broad categories of symmetric ciphers. There are stream ciphers and block ciphers. The stream ciphers are like the one-time pad, meaning that we are going to generate a string of bits that look like a random string of bits. We generate that, and then the actual encryption. How do you encrypt with a one-time pad? What's the process?
You match every single...
Starts with an X, ends with an OR. XOR, right? You just XOR the bits together, right? So when we talk about stream ciphers, the issue is how do you generate that string of bits, right? So we will take a short, relatively short, symmetric key. We'll stretch it out into a long string of bits that we will call a key stream. We'll use that key stream exactly like we use a one-time pad, meaning we simply XOR to encrypt. We XOR the same thing to decrypt. So with a stream cipher, it's all about how do you generate that string of bits? How do you generate that key stream? Encryption is trivial. It's just an XOR, all right? Okay, in block ciphers, these generalize a code book. Now, if you have a code book cipher and you give everybody the code book, it's not a very good cipher, right? Because everybody knows what the code book is. So what's going to happen with these block ciphers is there's a key. Okay, there's a symmetric key, and this key, in effect, creates a new code book. Every time you change the key, you get a new code book. There's a process to generate plain text and ciphertext, but from a high-level perspective, what's happening is you have a huge number of code books, and they're indexed by the key. Choose the key, and as long as you use the same key, you sender and receiver are using the same code book. Use a different key, it's a different code book. Okay? So it's like having a huge number of code books that are indexed by the key. Okay, I just want to look very briefly at a couple of classes of stream ciphers. There's sort of two types of, there's stream ciphers, but there's a couple ways to construct stream ciphers. And these used to be very, very popular, okay? Most of the bits were encrypted with stream ciphers. And that was because these are things that you can build in hardware. So it's very fast to encrypt bits with a stream cipher. In the past, processors were slow, so you couldn't do things in software and encrypt at high rates of speed. And I mean, you know, high rates of speed today are different than high rates of speed then, okay? So back in the day, if you wanted to encrypt, say, audio, it was typically like 56K, you know, 56,000 bits per second, which is very small by today's standards. But then to do that, you had to actually build a hardware, special purpose hardware device. Okay, and so these ciphers, these stream ciphers, are designed generally to be built in hardware, with the one notable exception that we will talk about. So I just want to talk about one specific stream cipher. There are lots of stream ciphers. Okay, this is one that we will see again later and just sort of illustrates the class of ciphers. Okay, so this one's called A51 and it's used in the GSM cell phones, which we will talk about that security architecture later. Okay, so think of your hardware class where you have you have logic gates and all that sort of stuff. Okay, think like that here. So we have 3 shift registers. Okay, and these hold 19, 22, and 23 bits, which adds up to 64 bits. So the key, right, the symmetric key that Alice and Bob share is 64 bits, and those are the bits that go in these registers to start with. Okay, so a 64-bit key. Okay, 64 bits. What do we do with those? We want to stretch that 64 bits out into a long key stream that we then use to encrypt, right? We do encrypt by XOR, so the decryption is boring, so we're just talking about how we generate the key stream from these 64 bits. Okay, it looks terrible, it's not that bad. We'll get to the picture in a second. What we do is we look at these 3 special positions, one in the X register, one in the Y, one in the Z. We take the majority. They're bits, right? So they're either 0 or 1. So there has to be more zeros or more ones. whichever it is, more zeros or more ones, that's the majority. Then we look at each of these individual registers and we see if that special bit is in the majority. If it is, that register steps. If it's not, that register just stays the same. Stepping just means you do some XOR, you shift the bits over and put a new bit in. The pictures, and then when you're done, to get the actual key stream bit, you XOR the 3 rightmost bits. Okay, this looks like a lot of work to generate one single bit of key stream. But the beauty is you can do it over and over and over and over indefinitely, right? And in fact, you can make this very fast. You can make this basically at each clock cycle. You can generate one bit of key stream. Okay, so the picture is worth 1,000 words, right? So you have 64 bits. These are all bits here. Okay, initially you put in the key, but it changes over time. You just use whatever's in there at a particular time. You look at these 3 special bit positions. You take the majority. Then you look and see, is this guy in the majority? If it is, then you XOR these 4 bits together, put the value in here, and shift everything over. If it's not in the majority, it just stays. Nothing changes. And do that for each of the registers. When you're done, take those 3 bits at the rightmost edge and XOR them together to get your bit of key stream. For example, suppose at some point in time the registers are filled with these values. Okay, what's the first thing we do? Find the majority of those red positions. Those are the special positions. So what's the majority? Well, I have 1, 0, 1. Are there more ones or more zeros? There are more ones. Okay, it's not a trick question. Okay, more ones. So this register is going to step. This register is going to step. This one's going to stay the same. Doesn't do anything. Okay. What does it mean for this register to step? It means I will take these 4 bits and XOR them together. That's 0, 1, 0, 1. When you XOR them together, you get, it's just an even or odd thing, right? Okay, so it's even, so it's 0. So I get a 0. So I shift everything over and put a 0 here. Got it?
Why those 4 specifically?
That's the way somebody designed the algorithm. That's the way we do it, right? That's a great question. We'll talk about that a little bit when we get to it. Yeah, it's the same. That's specified as part of the algorithm. We don't get to choose that. Okay, this one, because it's not in the majority, it just stays. Okay, so nothing happens. This one, because it is in the majority, we do that stepping thing. We XOR these 4 bits, 1, 0, 0, 1, and again, that's 0. Shift everything over and put a 0 there. Okay, now to get the key stream bit, what do? This one shifted, so now there's a 0 there. This one still has the 1. This one has a 0. 1, 0, 1. Sorry, 0, 1, 0. XOR 0, 1, 0 together. What do I get? What's a 0 plus 1 plus 0? 1, right? So I get a 1, and that key stream bit is 1. And then just keep going. You can do it over and over and over and over. So I can take that 64 bits I started with, and I can get as many key stream bits as I want that I will XOR to encrypt and decrypt. All right? Okay, so that's all this is saying. Get the majority, step 2 of the registers, XOR those 3 bits together, and you get 1 in this case. All right. Okay, so shift registers were necessary because you had to do things in hardware in order to get the speeds that were necessary to encrypt data. And they're not really designed to be implemented in software, so if you try to write this out in software, it's going to be relatively slow. And in the past, they were certainly very popular, but today you can do so much, you can really do things in software that have the speed that you need to encrypt, millions of bits per second. So these things are kind of a losing favor. You don't see too many of them, but in resource-constrained devices, they still do make sense, okay? And there are cases where these ciphers do get used today, and we'll even mention a few of those, okay? Okay, so if you remember last time we started talking about symmetric ciphers, okay, the real-world ciphers, things that are used in practice. And we talked about stream ciphers and block ciphers. Okay, so there's two broad categories of symmetric ciphers that are used in the real world. And amongst the stream ciphers, typically they involve shift registers, right? So if you think back to your hardware class that you took and logic gates and all that, that's the way that they're set up because it's very fast to encrypt in that way. Now, it's kind of awkward to write them in software and try and, even to look at them, they look, horrible and whatever, but they're just generating key stream bits. Okay, they're just taking a key, stretching it out into a long pseudo-random string of bits that can then be XOR'd with your message, right? So that's how you encrypt. You generate that same key stream, you XOR it to the ciphertext, you get back the plaintext, just like a one-time pad, right? So when we describe those ciphers, we just describe the process of generating the key stream. We don't talk about the actual encryption, decryption, because it's just trivial. It's just XOR, just like a one-time pad. Okay, and we looked at one specific example, and that was A51, because we will see that one again. But there's lots of ciphers like that, okay, that involve shift registers. Okay, now, so those things were needed in the past because you had to have high speed in order to encrypt, and software was slow, processors were slow. So that was the only option. Okay, today there are other options and other things tend to work better, so they don't get used that much. But in resource-constrained devices where you don't have much computing power, it still makes sense, and you do see stream ciphers in those sort of environments. Now, another stream cipher, which is actually very unusual for a stream cipher, is the RC4 algorithm. I want to present that very quickly here. This is known as Revest Code 4. Ron Revest, we're going to hear his name over and over, probably the most famous cryptographer ever in modern history. Revest and Shamir will be two names we hear again and again. And here he is in this stream cipher domain. So he created this cipher. Now, if you look up on, say, Wikipedia, and you look up how to generate a random permutation, there's an algorithm to generate a random permutation. If you look at that, this cipher was clearly modeled after that. Okay? It uses a similar approach, but a cipher has a key, right? Generating a random permutation, you don't have a key. So there's a key here. We have to take into account the key and how do we generate the key stream and all that. But it's the same sort of approach. All right. Okay, so what we're going to do is we're going to have a key here, and our key can be any number of bytes. So everything in this is in terms of bytes, not bits. Okay, so it can be any number of bytes, 0 to 255. We have a lookup table. Okay, really the entire structure of the cipher is just a lookup table. It's a table that consists of a permutation of all byte values. So it's a table of length 256. And it's always a permutation, meaning every byte value is in there, it's only in there once. Okay, no repeats, nothing missing. All right, so we have to initialize that permutation. We scramble it using the key. Then at each time we want to encrypt something, we pull a byte out of that table and we use it to encrypt our message. Okay, we use it to encrypt a byte of our message or decrypt a byte of our message. When we pull a byte out of that table, we permute some elements in the table. By permuting a permutation, you get another permutation. So anytime we swap, anytime we swap elements in a permutation, we still have a permutation. So by just using swaps in this cipher, we never lose that permutation property. All right, so that's kind of the key observation here. Okay, now the nice thing about RC4, a couple nice things, is that it's designed to be written in software. Okay, that's very unusual for stream ciphers, so it does get used a lot because of that. And it also produces a byte at each step. Okay, instead of something like A51, which just produces a single bit. So we get a whole byte, 8 bits at each iteration here. Okay, so here it is. So we have to initialize the permutation, right? We have this permutation. The permutation is S. I'm just going to initialize S to be 0 through 255. That is a permutation. It's a very boring permutation, but it is a permutation. So I just initialize it 0 through 255. Now I have a key. and it is n bytes. It can vary from 0 to 255. No, 0 wouldn't be very good, but 1 to 255 bytes. Whatever length it is, let's call that n. All this is doing is creating an array k, which just repeats that key over and over until it fills up an array of length 256. Okay, that's all that's happening here. So it's just very basic initialization. Now I'm going to actually scramble this permutation s. And the way it gets scrambled is that you take this index I and it just steps regularly through, 0 through 255. The index j depends on what's in the permutation at any given time and the key. So I get two indices. And then I take those two elements that correspond to those indices and swap them. Again, by swapping elements, I still have a permutation. So this S is always going to be a permutation. Once I'm done with that process, I reset these indices I and j to 0. Okay, that's just the initialization. Okay, I've just scrambled that permutation. Now when I actually want to encrypt or decrypt, I want to pull elements out of that table S. Okay, and the way I do that is I take this index I and I increment it by 1. And I have to loop around to make sure I stay within the bounds of the array. And I take the index j and I increment, and I take the old value and I add to it some element from that table. All right? That gives me two indices. I swap those two elements in the permutation. It's still a permutation, right? And I use those two to get an index, and that is what I use to grab the key stream byte that I will use to XOR, to encrypt or decrypt. So notice there's kind of a level of indirection here, right, to get this index that you're pulling out. There's a couple of things going on here. One is kind of this indirection, but also the table itself changes. Every time I get a byte out of this table, the state of the system changes. So if you're a cryptanalyst trying to break this, the target is to figure out what's in S, right? You want to know what that array looks like. So if you can get it at any one time, you're good. You can determine the key for the rest of the times, but it's constantly changing. So it's sort of a moving target that you're trying to get here. Okay, but I mean, it's pretty simple, right? I mean, it's 10 lines of code to initialize, and then it's 5 lines of code, 6 lines of code to actually generate key stream. So every time you want a byte, you just do this. Okay, it's very fast, very efficient, and it's considered pretty strong, provided there's sort of a technicality here. The first 256 key stream bytes that you generate have some potential weakness to them. So what people do in practice is, after doing this initialization, okay, after doing this, okay, then they will do this 256 times and just throw away those bytes. And then they actually start generating the bytes that they want to use for encryption and decryption. As long as you do that, it's considered a pretty strong cipher. Okay, so bottom line on stream ciphers, they were certainly popular in the past. They were needed. They were often generally built in hardware, and they needed that sort of speed to encrypt things like voice. Even 56K, voice typically 56K was too much for things done in software. But today that's not true, right? Processors are extremely fast, and we can encrypt megabytes per second, right? So we don't really need these stream ciphers for many typical applications. Okay, and what about the future of stream ciphers? Well, I saw Shamir, the other big crypto guy, I saw him give a talk several years ago, and he declared the death of stream ciphers. We don't need stream ciphers. We can do everything with block ciphers. But I don't think that turned out to be true, right? Okay, because we do see them still today in, as I mentioned, resource-constrained devices. Okay, if you want to do more with less computing power, stream ciphers often make sense in those environments. Okay, so that's it for stream ciphers. On to the big one, the big enchilada here, block ciphers. Okay, block ciphers are really the king of encryption today. Okay, the vast majority of bits that are actually encrypted in the real world, probably well over 95%, maybe 99% of all the bits that get encrypted in the real world are encrypted with block ciphers. Okay, so these are the kings of cryptography today. we'll see, the public key systems don't encrypt very many bits, but they're very important. Okay, they do have an important role to play, but as far as quantity, these guys are the winners by far. Okay, and these really are, if you keep in the back of your mind, these are really just codebook ciphers. Okay, it's just a codebook cipher. You take some block of bits in, you get a fixed block of bits out, as long as the codebook doesn't change. But there's a key, okay, and the key changes the codebook. So as long as you leave the key the same, you're working with the same codebook. You change that key, it's a different codebook, okay? So it's sort of like you don't just have one codebook here. I have a huge number of codebooks all indexed by this key. Wow, that's great. I have as many codebooks as I could possibly want, all right? Well, of course, to implement these, we have to have some algorithm. We can't have a huge code book. It's a huge table, right? I can't even store that many bits, right? So I have to have some way to sort of generate this on the fly. And the way this is going to, at least the technique we're going to talk about, involves a so-called round function, not because it's round, but because we iterate it for multiple rounds, okay? Okay, you'll see here in a second. So the input to each round is the output from the previous round plus some key, some part of the key, all right? And these are designed to be implemented in software, okay? And they're very, the speed is a part of the design of such ciphers, right? It's a factor. Okay, I want to look at one specific type of block cipher, and this will be the Feistel cipher. Okay, and of course it's named after a person, Feistel. And this is not a specific cipher. It's not like RC4, it's not like A51. This is a general class of ciphers. This is a way to construct a cipher, okay? Clear on that? It's not a specific cipher. It's a generic approach to building a block cipher. Okay, so to construct a Feistel cipher, you have your plain text block, right? Because we're encrypting the plain text in blocks. Each block is like the word in the code book, right? We're going to get another block out. It's going to be the same number of bits, okay? So we have a block of bits go in, and we're assuming here it's an even number of bits. We split it into a left half and a right half. Left half and a right half, okay? All right. And then we do this for n rounds, okay? This again is specified as part of the algorithm. You will have to know this formula, okay? L sub I is equal to R sub I and all this. Just think of it in words, okay? It's much easier, at least I think it's much easier to remember this in words than to try to memorize the formula. Okay, what this says is what? It says the new left half is the old right half. So whatever the right half was, just copy it to the new left half. Okay, that's trivial, right? The new right half is the old left half XORed with a function of the old right half and the key. Okay, got that? Just say it in words, okay? Say it over and over and you will remember. All right? So that's how we update. That's the round that we go through. Now notice we didn't specify, and it's just an XOR, right? We didn't specify this function f. So this technique will work for any function f, right? We can put any function f in there that produces the right number of bits, right? So it makes sense. It will work formally, but it's only going to be secure for certain functions. So all the analysis about whether this is secure or not comes down to looking at that function. Yeah. Yeah, you have a question?
Is it because it's like sequential because we read from left to right?
What's that?
We read from left to right, is that so?
You'll see the picture here in a second. Yeah, I mean, however you define left half and right half doesn't really matter too much. Yeah.
Wait, so what does it mean for each round? Like what dictates how many rounds there are?
There are n rounds in this case, so that's a parameter. When you're designing this, you decide how many rounds you want, you decide how big a block you want, you decide what that function is, and then you plug it into this approach, to this technique. Okay? Okay, when you do this for n rounds, whatever comes out at the end, we'll call that the ciphertext. Well, okay, so we have plain text, we know the key, we produce ciphertext, right? If we know the key, we have to be able to take that ciphertext and get back to plain text, or people are not going to like your cipher very much, right? Okay, so how do we do that? Can we run this backwards and get from the ciphertext back to the plain text? assuming we know the key, right? These K's that go in here, and the F. Of course, we know how the cipher works. We know N, we know F, right? Everybody knows that. That's Kirchhoff's principle. Well, yeah, you can actually just run this backwards, okay? Why can you run this backwards? Well, I mean, look, what does it mean to run it backwards? You want the indices to get smaller, right? So just put this over on the left-hand side. That's easy. Jeez. R sub I minus 1 is equal to L sub I. You just step backwards, right? Okay. What about down here? How do I run this backwards? Well, this is an XOR. I don't want this XOR on this side. How do I move it over to this side? I really just want to solve, right? I want to solve this for R sub I and L sub I minus 1, and then I can run it backwards. How would I do that down here? What's the property of XOR that we've used over and over? XOR is the same thing with itself. It goes away, right? So just XOR FR on this side and XOR the same thing over here, and you solve for this. Okay, so that's all you do to run it backwards. So this just says start with the ciphertext, step from N to 0, N minus 1, N to 1, sorry, and just follow this formula, and you have to get back what you started with. This assumes, of course, that you know the key, right? If you know the key, you can encrypt and you can decrypt. Okay, that's the algorithm. That's how it works. But a big picture, it's still just a code book, right? Because you're taking a block of bits in, you get a block of bits out. If the key doesn't change, that same block of bits will always produce the same block of bits out, all right? So it's acting like a codebook cipher in the larger sense. Okay, so again, this will work. This formally will work for any function f you can put in here that, you know, meets the basic criteria, but it's only going to be secure for certain functions f. All right. Now I want to talk about a specific Feistel cipher. Okay, the Data Encryption Standard, or DES. This was developed in the 70s. Why would people suddenly need cryptography in the 70s? What was going on then? This is the computer revolution, right? Before the 70s, nobody had computers. You know, your private important information was stored in the doctor's office on a file, you know, 3x5 note card. And so, you know, what's to protect, right? Just lock the filing cabinet, right? But now people have computers. They have floppy disks. It's those things at the Computer History Museum, floppy disk, right? Put it in, and there's thousands and thousands of users' information on this one little floppy disk, and you got to protect that, because if somebody gets that, my God, you know, all that information's exposed. And so people started to realize, okay, we need some way to protect data. Confidentiality and integrity are important concepts for computerized data, but nobody knew how to do cryptography. Because at that time, the only people who did cryptography were governments and militaries, right? And they're not talking, right? So there was a lot of sort of snake oil sort of solutions to cryptography. Okay, people were trying to sell crypto systems that were just garbage. You know, they weren't any good. And nobody knew how to even judge whether these systems were any good or not. So the US government decided, we're going to create a standard. Okay, and this standard is going to be required if you're dealing with the US government. And it will, because of that, it will become a de facto industrial standard, right? Okay, just because the government does so much business, right? Okay, so the US government proposed this standard. So there's a NIST, if you've heard of NIST, National Institute of Science and Technology. At that time, it was called the NBS, National Bureau of Standards. They put out a proposal. And they said, okay, send us your crypto system, send us your ciphers, and we're going to pick one. It's going to become a national standard. Wow, I mean, come on. If you're a cryptographer, you can now be world famous because your crypto system is going to be selected, you know, by the US government, and everybody's going to use it. So how many ciphers do you suppose they got that they had to judge? One. They actually got very few, okay? Literally like a handful that were plausible. I mean, they got a few, but some of them were crackpot things. They got a handful of them that were actually plausible. Why so few? Because nobody was doing cryptography, right? Nobody had a clue, right? So nobody really knew what to do. but there was a small group at IBM. IBM has a research lab, Bell Labs, not Bell Labs, but IBM had a research lab, and they were doing research on cryptography. So they had a small group that was working on cryptography. So they submitted a cipher that was called Lucifer. All right, and this standard is, and so here's the way it actually works. So the National Bureau of Standards put out this proposal: send us your ciphers, and we're going to pick one. They get these ciphers, they look at them, and then they suddenly realize, hey, we don't have any expertise in cryptography either. We don't have any way to judge whether these are any good. So they went to who in the government has expertise in cryptography. It's the NSA. So they went to the NSA and they said, okay, you got to help us judge, decide whether these ciphers are any good or not. And the NSA said, no, we don't do that. We're secret. We don't. At that time, they were super secret. They even deny the agency even existed, right? So they refused to help out. But that didn't last because, some congressman said, okay, we're spending billions of dollars here. You got to help them out, right? So they said, okay, we'll help out, but don't tell anybody. Can imagine how that turned out. Okay, so NSA was secretly involved. And what happened was they took this Lucifer algorithm and they made changes to it. Okay, there were, it was clearly the best algorithm that was submitted, but they made some subtle changes and some not so subtle changes to the algorithm. So NSA was secretly involved, and all people saw on the outside was the Lucifer algorithm that came in to NBS and the DES algorithm that came out, and they were different. And so, of course, people are going to ask, why are they different? And the NBS says, well, we can't say. It's secret. And people didn't like that, right? So people got very fired up and started studying cryptography. This is like a huge watershed event in the history of cryptography. Before this, only governments and military are doing cryptography. And the NSA, by trying to stay out of it and trying to be secretive about it, they just made it, did exactly the opposite. Okay, everyone started to study cryptography, and there's a huge amount of cryptanalysis been done on this cipher. It spurred whole fields of development in the area. Now, academic people do cryptography, industry does cryptography, everybody does cryptography. Okay, so we want to look at DES in a little more detail. So again, DES is a Feistel cipher. Okay, so it has that new left half, his old right half, all that stuff. Okay, has to be in here. The block length is 64 bits. So we take 64 bits in, we've produced 64 bits out. The key is 56 bits. There are 16 rounds, all right? Each round, we select 48 bits of these 56 in a specified way. Okay, there's an algorithm to select specified 48 bits each round. The round function, believe it or not, is relatively simple for a block cipher. And the security here is going to depend on these so-called substitution or S boxes. Okay. Now, I'm going to show you the picture. Next slide. Don't faint. Okay, it's not as bad as it looks. We break it down. Okay, it's not really that complicated. So this is one round of DES. Okay, each of these lines, the number represents the number of bits that goes on that wire. All right. Now, the whole part over here, this whole part over here, is just the algorithm to take the 56 bits of key and select the 48 that you want to use in this round. That's boring. Okay, so we're not even going to talk about that. There's just a specified way to take 56 bits and select the 48 you want. So that's the 48. So forget that part. Okay, this is the part we want to talk about. This is a round. There's 16 rounds to encrypt a single block. So you start with the left half and you start with the right half. Okay, I claim it's a Feistel cipher. What's the definition of a Feistel cipher? Well, what's the new left half?
The old right half.
It's the old right? Well, that's true, right? We just bring down the old right half and we put it here as the new left half. That's trivial. What's the new right half? According to a Feistel cipher, it's the old left half XORed with a function of the old right half and the key. Okay? So this is that function F. This is what represents that function F. There's just three operations there for, and I count. There's this so-called expansion permutation. There's an XOR with the subkey. There's these S boxes, these substitution boxes, which are really the crucial ingredient here. And then there's another permutation. All right, so that's that function f you see in a Feistel cipher. Okay, so all we have to do to complete the description of this cipher is tell you what does this expand, what does it do? XOR is self-explanatory, it's just an XOR. S boxes, we have to tell you what those are and what's this permutation. Okay, that will tell us exactly how this cipher works. Okay, so what's this expand business? Well, notice 32 bits come in and 48 bits come out. Okay, so if we number those 32 bits that come in, 0 through 31, these are the 48 bits that come out. So all we're doing is just repeating some of those bits twice, right? To get up to 48 bits. So nothing fancy. Okay, you're just sort of permuting the bits around and putting some of them in there twice. That gives us 48 bits. Once we get those 48 bits, those are XOR'd with the subkey, right, that came in here. So now I have 48 bits, and I have to squeeze that back down to 32. So how do I go from 48 back down to 32? That's the job of the S boxes. There are 8 of these S boxes. Each of them takes in 6 bits and spits out 4. Okay? And these are specified, again, as part of the algorithm. You don't get to choose them. They are there. They're specified. Okay? Here is one of the S boxes. Okay? This is one of the S boxes. We have 6 bits going in, right? We take the first and last bit of those 6 bits, and that indexes the row. We take the middle 4 bits, and that indexes the column, and then we pull out the 4 bits that happen to be there. That's all it is. It's just a lookup table, right? Okay, nothing fancy. So I mean, suppose the bits that, if I had a marker, suppose the bits that come in are 1, 1, 0, 0, 0, okay? So we take the first and last, that'd be 1, 0, right? I get this. And the middle 4 bits were 1, I think, if I can remember correctly, 1, 0, 0, 0. So I go over there, where's 1, 0, 0, 0? Right there, and I pull out 1, 1, 1, 1, 1. So 6 bits in, 4 bits out. Just a lookup table, all right? So does anybody see what's going on with each row of this lookup table? Each row of this lookup table has some special property that it satisfies. So when we talk about ciphers, we seem to be constantly talking about XOR, and we also talk about permutations. So if you look carefully, each row of this is just a permutation of 0 through 15, or 0, 0, 0 through 1, 1, 1, 1. Each row is just a permutation of those 16 values. And that's true of all 8 of these S boxes. Every row is just a permutation of those values. So I mentioned that, well, let's finish the description. Okay, so we get 48 bits in, each of them split into groups of 8, 6 bits, sorry, 8 groups of 6 bits, and each of those gets squeezed down to 4. 4 times 8 is 32. Now I'm down to 32 bits, and there's a final permutation. Just permute those 32 bits, whatever comes out, that's it. Okay, that's the end of that round. I've defined the round function. Now the subkey part, I'm not really going to go through. It's kind of boring. Okay, but we have an algorithm and we produce those 48 bits. You could just hard code it in. Which 48 bits do you want to select in each round? It's part of the algorithm. Now there's a little bit more to this. We don't describe these things in detail because they don't have anything to do with security, but they are part of the algorithm. So if you want to implement DES, you have to do these things. There's some initial permutation before the first round. The halves get swapped after the last round. That's just for efficiency. And there's a final permutation and so on. But none of this is really relevant to our purposes. But you would have to do those things if you want to call it DES. It has to satisfy all these requirements. Okay, so I should go back here and just mention we mentioned that the Lucifer algorithm, okay, this is what IBM produced, the DES algorithm, that's the things that NSA changed. Okay, people were suspicious, right? NSA does 2 things, right? They don't only create ciphers for the US government, but they break ciphers. So people were thinking, well, maybe they put a back door in this cipher so they could break it and nobody else can break it. So I want to figure out why they made these changes to this particular cipher. Some of the changes were obvious. They reduced the key from 128 bits to 56 bits. Well, that's a huge change, right? So, there's a reason for that. They did that. But the subtle changes were even more baffling to people. And the subtle changes were all in terms of these S boxes. Some of the permutations that showed up here were changed to other permutations. Why did they make these changes? Why would they change certain permutations to something else? And that's what sort of spurred the analysis and the work in cryptanalysis was to try to figure out why they made those changes. Okay, so what about the security of DES? Is there a backdoor in this cipher? Was there some trick here that NSA pulled? Well, these S boxes are really crucial. Okay, everything else in DES is linear. If you didn't have those S boxes, you could literally write down linear equations and you could solve for the key. Okay, and that would be very bad. You could break the cipher relatively easily. There's been almost 50 years now of cryptanalysis of DES, and nobody's found a significant weakness in the cipher. There's a few minor things that people can do to reduce the work factor a little bit, but basically it's an exhaustive key search to break DES. All right, there is really no significant shortcut. So the conclusion is whoever designed this knew what they were doing, and in fact, it's more resistant to certain cryptanalytic attacks that were unknown on the outside than the original Lucifer cipher. So the people at the NSA who made the changes, they made it better, not worse. Okay, that's yeah.
So you used to work at NSA.
Yeah, not at that time though. It's way before my time.
Did you still look at an NDA, non-disclosure agreement?
Yeah, I mean, actually, you're technically required to, like if I do a research paper that relates to anything I worked on there, I have to get it approved by them. That's why I work in a different research area now. Okay, so that's it for DES. Block ciphers, we do need some notation. Yes.
Sorry, can I ask a question about DES though?
Sure.
So the S boxes, that's known to the attacker, right?
Yes. Yeah, I mean, it's specified as part of the algorithm.
So I thought you said that if they know the S box, then they're able to just solve for the key.
No, if you did not have S boxes in it, that's a nonlinear operation. If you leave out the S boxes, right, from DES, everything in it is linear. If you take a linear algebra class, you can set up equations and solve, and you would have the unknowns there would be the key, and you could solve for the key. So you have to have some nonlinear operation in any cipher like this, and that's what the role that the S boxes play.
Could you go into more detail what a nonlinear?
It just means you can't write down linear equations to solve it. That's really all it means, right? I mean, just think of your linear algebra class. You write down systems of linear equations. Mathematicians are very good at solving those. If you have nonlinear equations in there, it's very hard to solve, right? Okay, so we do need some notation for block ciphers. So we'll use capital P to represent a plain text block. Okay, it can be, it depends on the cipher. Those block sizes can be different for different ciphers. Ciphertext block, these are always the same size, plain text and ciphertext in all ciphers we consider. We will use this capital E to represent encryption. So we encrypt a plain text block given a particular key, and we get ciphertext. Of course, we can use D to represent decryption. So we decrypt the ciphertext up here with the same key K, and we get back the plain text that we encrypted up here. And that's what this shows. Okay, these are inverse operations, right? You encrypt with the key and you decrypt that result with the same key, you get back the plain text you started with. And that makes sense in the codebook sense, right? Because you're looking it up in the same codebook. You're encrypted with a particular codebook, you look up in the same codebook to decrypt. And this is just saying you can go the other way. You can decrypt first and encrypt and you get back what you started with. But notice here, if you have different keys, right, it does not work, okay, because those are different code books. It's as if you encrypted with one code book and now I try to decrypt with a different code book. That's not going to work, okay, in general. So those keys have to be the same to encrypt and decrypt. Okay, now DES was developed in the I think 1977. It became an official government standard, and as predicted, everybody started using it. Very popular. There was no real alternative at the time. In spite of the controversy, it just became a de facto standard. All right. Fast forward to, say, the early 90s, and people could break DES. There was actually a group that constructed some special purpose hardware and did an exhaustive search and cracked DES, in a couple of days, something like that. So it was considered insecure as early as the 90s. But people liked DES. They were using DES. Okay, so is there a way that we can make DES more secure? And there is a standard approach to do that. It's called triple DES. Okay, and this still gets used some, probably shouldn't, but still does get used some. So 56 bits was really the problem. Okay, the key itself was just too short. You could do an exhaustive search over it. Okay, so to overcome that, and DES is everywhere and people want to use it, people came up with this approach called triple DES or 3 DES, and it will have a 112-bit key. Where does 112 come from? Well, of course, triple, right? So 3 times 56 is 112. Oh, wait, that's not right. It's 2 times 56. So why isn't it called double DES? We'll see here in a second. Okay, so here is the definition of triple DES. You generate 2 DES keys, and the encryption and decryption here represent DES, okay, that specific cipher. Okay, it's DES, just DES, okay? Okay. So you take the first key, you encrypt your plain text with that key, then you decrypt with the other key, and then you encrypt again with the same key. So 2 keys, 3 DES operations, triple DES because 3 DES operations. Can we decrypt? Okay, assuming we know the key, we have the DES cipher, can we decrypt? Say yes, just start on the outside here, decrypt with K1, okay, then encrypt with K2, and then decrypt with K1, right? And that's all that's going on here. You get back the plain text. So you can encrypt, you can decrypt, and you get a key that's 112 bits instead of 56. So it doubles the key length, which exponentially makes the work factor exponentially greater, and no one can do an exhaustive search on a 112-bit key. Okay, but the question is, why 2 keys here? Why not 3? Right? We have 3 operations. Why not put 3 different keys in there, right? Then we could make the key 68 bits. So why do you suppose they chose two keys here? Well, the answer is certainly not obvious. The answer is backwards compatibility, believe it or not. So suppose you design your system to use triple DES, but somebody you're communicating with only uses single DES. You can choose these 2 keys to be the same in triple DES, and it just collapses down to single DES, but it's 3 times as slow. So I don't know who would actually do that, but that's the rationale they give. Yeah.
Assuming there was a 3rd key, could you just make all 3 keys the same to achieve the same purpose?
If you made all 3 keys the same, then it's still just a 56-bit exhaustive search, right?
Right, but I mean, if you need it to be backwards.
Yes, that's true. Okay, so that doesn't really explain why there's only 2 keys. It does explain why they did this encrypt, decrypt, encrypt thing, right? Okay, so what about that? 3 keys. Why don't we have 3 keys? Well, okay, why don't we do something like this? Just encrypt twice with the same key. Okay, that would be stupid because that's just a 56-bit exhaustive search, right? Because that doesn't solve the problem, so that's not good. Why not this? Okay, why that 3rd operation, right? Because if we're only going to use 2 keys, that 3rd operation just slows everything down, right? Makes it much slower. Well, we're not going to go through the details here, but there's actually a kind of meet in the middle sort of attack that you can do. And the work factor to do an exhaustive search in this case is almost the same as with a single key. So you don't really gain anything using 2 keys, using 2 operations. You do need that 3rd operation in there. It's actually essential. Okay, but again, we won't go through that. It's known plain text stacks, a little bit involved, but not really that complicated. Okay, to finish, I just want to discuss very quickly here the AES, the Advanced Encryption Standard. So DES was a standard from the 1970s all the way up until, I don't remember when the AES happened, late 90s, maybe early 2000s when it was officially approved. So they had another competition, right? Now they realized DES is weak, so we need a new cipher. This one, NSA was openly involved. There were several different groups, were openly involved in this process. I actually worked there, and I remember a little bit of this. So what the process was actually really clever, I think, the way it was designed. They said, okay, cryptographers, send us your ciphers, and we're going to pick one. It's going to be the advanced encryption standard. You're going to be a world-famous cryptographer. This time, instead of like DES, where they got like a handful of ciphers, they get a large number of very good ciphers, right? Because there's lots of people doing cryptography. So how are they going to decide which of these is best? They had a set of criteria they were going to follow, but the way they ran the process, I thought, was really clever. So what they did is people sent in their ciphers, right? And then they had conferences. Okay, they would invite, they narrowed it down. Okay, to start with, they narrowed it down to like a dozen ciphers. Okay, so they got a dozen ciphers. So they have a conference, and they bring in all the people who design these ciphers. And all these people who design these ciphers are trying to break the other guy's cipher, right? Because they want to be the famous cryptographer, right? And so you get these world famous cryptographers working to break each other's ciphers, and really a huge amount of effort was put into analyzing those ciphers in a very short period of time. And then they cut it down to 5, and they did it again, right? And so they had like 5 ciphers. They were all pretty strong. They probably could have selected any of them. Came down to splitting hairs, which one's more efficient, so on and so forth. And they selected this particular algorithm, which is pronounced Reindahl. I think it's 2 Belgian cryptographers. I get this wrong. I put this on a video once, and I said it was Dutch cryptographers, and I got some angry Belgians commenting, it was Belgian cryptography. I think it's Belgian. Okay, so I don't know, what's the difference? Those countries are all so small, who cares? So anyway, I think they're Belgian cryptographers. They submitted this algorithm that was selected. And it's an iterated block cipher like DES, but it's not a Feistel cipher. Okay, the beauty of a Feistel cipher is what? The beauty of a Feistel cipher is no matter what you choose for that round function, you can always decrypt, right? Just the process itself allows you to decrypt. But what's the downside to a Feistel cipher? Okay, that's a positive. There's always a trade-off, right? So that makes it easy to decrypt. What about the downside? Is there any negative to a Feistel cipher? Well, if you think about it, what's that process? New left half is old right half, new right half is blah, 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 right? Well, half of the bits each round don't get changed at all, right? You just bring down those and put them here. They're not changed at all. So you have to do essentially twice as many rounds to affect all of the bits in equal amount, right? So efficiency matters in this competition. So the winner of the AES competition, they chose not to do a Feistel cipher. They want to affect all of the bits each round. Okay, that's great, but the downside is now you have to worry about how do you reverse it. You have to make everything invertible, so it makes it much more complicated to design such a cipher. Okay, so just some parameters here. The block size in the official AES is 128 bits, although the Reindahl algorithm allows other sizes. The official standard, it only allows 128 bits. The key is variable length. It can be 128, 192, or 256. Okay. There's 10 to 14 rounds, depends on the key size. So longer key, you need a few more rounds to mix things up. Each round has these 4 functions in 3 different layers. They correspond to things in DES. Okay, there's nonlinear part here that corresponds to the S boxes in DES. There's a couple linear things here. Those correspond to the permutations that we saw in DES, kind of shuffle things around. And that's sort of the diffusion aspect, right? We're spreading the statistics around. And so just a picture here. These are sort of comparable to the S boxes, but they get implemented as a big lookup table. So kind of like the S boxes, you have this big lookup table in AES. There's these shifts. These are kind of comparable to the permutations that we saw in DES, and there's a couple of these things that happen as part of AES. And then there's an XOR, very much like what we saw with DES. You XOR the subkey in each round. And there's a way to generate which bits of key you use and all that. Now, the trick again is that with AES, you have to design these things to be invertible. With Feistel cipher, you don't have to worry about that. You just use the XOR. The magic of the XOR allows you to decrypt no matter what you choose for that round function. So here, the AES actually has a really cool mathematical description. You can describe all these parts to it in nice mathematical form. And so you can show that it's invertible, okay? So that's kind of cool. And finally, okay, promise this is the last thing, okay? We're going to talk about one more block cipher just very quickly. This one's not so popular. AES is very popular. You should use that. So, it's a very strong cipher. I just want to emphasize here that it's possible to create a relatively simple block cipher. And here's a relatively simple block cipher. T, the tiny encryption algorithm. In this cipher, we have 64-bit blocks, 128-bit keys, and it's assumed that everything here is a 32-bit integer. So if I do addition, subtraction, whatever, everything is within 32 bits. If you get carry into the next position, it's just gone, okay? So we can say that mathematically all the operations are mod 2 to the 32, but just think 32-bit integers, okay? Everything's a 32-bit quantity, all right? So the round function here is simple, but it's relatively weak, so we have to do a lot of rounds. Okay, that's the trade-off, right? Relatively weak round function, more rounds. AES is kind of the opposite extreme. Has fewer rounds for efficiency, but each round is relatively complex, right? Okay, and here it is. Here's encryption. The key, again, is 128 bits, so that's 4 32-bit words. Okay, the plain text is 64 bits, so the left half and right half are each 32 bits. And I have this magic number. Cryptographers hate magic numbers, so you have to tell them where it came from. So this is like the bits of the square root of 2 or something like that. So they tell you where, they just need a number, right? So they tell you where it came from. So it's nothing mysterious. And just go through this process. This process just consists of shifting, circular shifts, XORs, and addition. And all of that, again, is mod 2 to the 32, all based on 32-bit words. Do this 32 times, you get plain ciphertext out. You can reverse it, okay? You can go backwards. You can get the plain text from the ciphertext, assuming you know the key. All right, so is this a Feistel cipher? What do you think? Well, it's actually almost a Feistel cipher. The only real difference is right here we're using plus and minus, which technically is addition and subtraction mod 2 to the 32 instead of XOR. A Feistel cipher uses XOR. So it's just doing updating using addition and subtraction instead of XOR. So it's actually close, but not quite fitting the definition. Okay, so it's almost a Feistel cipher. It's fast, it's easy. There is some potential security issues, so I wouldn't recommend you use this in practice, but it does at least illustrate that it's possible to construct a pretty simple block cipher. Okay, so last time we finished up talking about specific ciphers. We talked about the DES cipher, okay, and that's really an important one historically. I don't think it's used much today. It certainly shouldn't be. But triple DES was around forever. It was used forever and ever, even after DES was long considered broken. We talked about the AES cipher. That's a very important cipher and very popular today. We talked about the T cipher, which is probably not so popular, but it does show that you can construct a block cipher that's relatively simple. Okay, so it is possible to do that. Now, what we want to talk about now is how you actually use a block cipher. And this is independent of which block cipher it is. It can be DES, it could be AES, it could be T, it could be any of 100 other block ciphers that do get used. Okay, when you use a block cipher, there's a few things you have to think about. Okay, we don't generally want to just encrypt a single block, right? We have a bunch of data that we want to encrypt. If you just want to encrypt a single block, I mean, that's 64 bits with DES or 128 bits with AES. That's really nothing. We need to encrypt a lot of data. Okay, so how do we do that? How do we encrypt multiple blocks with a block cipher? Well, I mean, think about it. If you needed a new key for each block that you want to encrypt, it would be totally impractical. This would be like a one-time pad because the key is usually roughly the same size as the block. Sometimes it's even bigger than the block size, right? With the T cipher, we saw that. Okay, so you have to be able to use the key for a lot of data. Okay, so you fix the key, that fixes the code book, right? So Alice and Bob share a key. Now they have this key, they know a code book, and they want to use this code book to encrypt a lot of data. All right, so how do you do that? How do you encrypt a lot of data with a code book? Well, we'll see. There's sort of an obvious way to do it, which is not really very good and probably you should never use. And there's a way that is sort of analogous to using a codebook cipher with an additive. And that's the way we really want to do it in practice. Okay, and then there's also a way to use a codebook cipher sort of like a stream cipher. Okay, so it does things that a stream cipher could do, and so that's why people think codebook or block ciphers, are everything today, and you don't really need specific stream ciphers, which I don't agree with quite, but that's part of the rationale for that. But anyway, you could also think about how do you deal with partial blocks. There's no guarantee that you end up on a perfect block boundary. We won't talk about that. That's not really that complicated. You could just pad, or you could do various other things with the last block. Okay, but we do want to talk about how you encrypt multiple blocks. Okay, so this is a pretty big deal. You have to be able to do this. You have to be able to deal with large amounts of data using the same key. You don't want to have to get new keys all the time. That's a very difficult process. Okay, so we'll talk about 3 modes. Now, there's actually lots of different modes that do get used with block ciphers, but CBC mode here is by far the most popular as far as I know, and so this is the one we will emphasize. And it's also important for another reason. We'll actually see this come up in 2 different applications. Okay, so you do have to know CBC mode. I can guarantee you there will be a question on the test about CBC mode, okay, because it's fundamental to both encryption and integrity, both confidentiality and integrity. And then we'll talk about counter mode, which is the way that a way to use a block cipher like a stream cipher. Okay, so ECB mode, electronic codebook. There you see codebook, right? Mode. Cipher block chaining. This is kind of like using an additive in a codebook cipher, in a classic codebook, and this again is how we use a block cipher, or sort of convert it into a stream cipher. Okay, so ECB mode. Remember our notation, right? So we have the big E here for encryption. K is the key, so the key is shared between Alice and Bob before we start any of this. How do they do that? I don't know. We'll worry about that later, but somehow or another they've shared this key and nobody else knows the key. So just Alice and Bob have the key, and it's secret between those two. So we have a symmetric key K. We have a bunch of blocks of plain text. We encrypt a block of plain text with the key K to get the ciphertext, right? And those blocks are the same size, ciphertext and plain text. So these blocks could be anything, but they're just bits, right? Everything's bits, so we split it up into fixed size blocks of bits. Okay, so we have a block P0, P1, and so on. Okay, well, the obvious thing to do is just use it like a codebook, right? You take the first block, you encrypt it with the key K, call that C0. You take the next block, P1, encrypt it with the key K, call that C1, and so on and so forth. Alice then sends those to Bob. Bob knows the key, so he uses the same cipher in decrypt mode with the same key. He decrypts the ciphertext C0, gets back P0, P0, so on and so forth, right? So this would work. This would be a way to encrypt blocks, send them from Alice to Bob, and you would be able to decrypt them as long as you know the key, all right? Okay, so everybody see that? Straightforward, just like a codebook. Once you fix the key, the codebook is fixed. It doesn't change. So you can use this codebook to encrypt as much data as you want, and you can decrypt it as long as you know the key. Okay, so again, the key K determines the codebook. You change the key K, it's a completely different codebook. Okay, so Trudy can spend forever trying to guess the key K, and she'll never stumble across the right one because there's too many keys, right? Okay, so this looks good. Okay, so I want to talk about an attack here, which is not really an attack. It's just a fact of life. Okay, this is a fact about codebook ciphers, and it's sort of easiest to see in the ECB mode, but it does come up in the other modes as well. Okay, so let's suppose the plain text is something goofy like this. Okay, Alice Diggs. I don't know why. This looks like something from the 60s. But anyway, so we have this Alice Diggs bomb, and there's a space at the end, so it comes out nice and even. And we'll assume that this is 64-bit blocks, like in DES, all right? And we're using 8-bit ASCII to encode the characters. So that means 8 characters represent 1 block of plain text or ciphertext, okay? So we can split this up into blocks, and when we do that, the first block is Alice and DI, and that far, and then the next 8 characters, and last 8 characters. So we have 4 blocks. Okay, so 4 blocks of plain text. Okay, so we're doing the ECB mode. So Alice and Bob share a key K. Alice uses that key to encrypt each of these blocks to get the corresponding ciphertext blocks. C0, C1, C2, and C3. She uses ECB mode. Just encrypt them with that block cipher using that key K. All right, so what does she do with these blocks? Well, she sends them to Bob, right? Bob is going to decrypt those blocks, and he's going to get back the message. Well, Trudy's in between here, right? And Trudy likes to cause trouble, okay? And so what Trudy's going to do, she doesn't know the key. She can't break the cipher. She can't read the message, but maybe she can cause trouble just by flipping a couple of blocks around. So she sends C0, C3, C2, C1. She just changes the order of the blocks. And so that's what Bob receives, and he has no way to know they're out of order. So he just decrypts these blocks thinking they're in order, and he gets the message, okay, which kind of changes the meaning, right? Okay, so what's the problem here? Did Trudy break the confidentiality of the message? It's an integrity issue, right? Okay, the confidentiality was protected. Trudy never read the message she was not supposed to read, but she broke the integrity of the message, right? When you receive it, you didn't know that it had been tampered with, and you decrypted it. So we have to do something else for integrity. This would be fine confidentiality-wise, but integrity-wise, we're going to have to do something else, okay, to protect the integrity of the message. So encryption alone is not going to be enough. We're going to have to think about something else for integrity. Okay, that's kind of generic. That actually comes up in lots of different contexts. We've seen it in terms of the one-time pad as well. You don't really get confidential. You don't really protect the integrity by encrypting it. There's lots of other contexts. But here's the actual weakness to ECB mode, and this is why you should never use ECB mode. Okay, suppose you have, so we assume Kirchhoff's principle, right? Kirchhoff's principle tells us what? Trudy knows everything, right? She knows everything here but the key. So she knows you're using a specific block cipher. She knows you're using ECB mode, among other things, all right? Okay, so in particular, she knows you're using ECB mode. Suppose in ECB mode, you have 2 plain text blocks that are the same. What can you tell me about the 2 corresponding ciphertext blocks? They have to be the same. You just looked up exactly the same thing in the same code book. You have to get the same result. Well, turn that around and suppose that Trudy sees 2 ciphertext blocks that are the same. What does she know about the corresponding plain text blocks? They had to be the same, all right? Well, is that a big deal? Or is this just something, anal retentive cryptographers would worry about? It is some information, right? You're giving away some information to Trudy. She knows these 2 plain text blocks are the same when she sees these 2 ciphertext blocks are the same. But is it something we really need to worry about in a practical sense? Well, I don't know. Think about it. Sometimes things in messages are known, right? Maybe the header part is known. You're encrypting email. The header is known, or the header is very stereotypical. So Trudy could know one of these blocks of plain text, and then she would know another block of plain text. Well, that's kind of bad. Or even if she doesn't know exactly what's in it, she would know this is part of a header, and here's another header. Okay, so I sort of know where the messages line up. Because that's a little bit of information, but maybe not super critical in a lot of applications. But, you don't want to give away that information if you don't have to. But it actually gets worse. Okay, it's actually much worse than that. Okay, the fact that the same plain text always encrypts to the same ciphertext. That's the weakness here. Okay, the problem with ECB mode. And just because of that fact, if I encrypt this image, okay, so on the left I have an image of Alice, and I encrypted this using ECB mode with, I use the T cipher here, just to pick a cipher. And when I encrypt it, it looks like that. So I'm supposed to be able to send that encrypted message, and nobody's supposed to be able to know what the original message was. But anybody looking at that's going to know what the original message was, right? So there's no confidentiality here. This is totally a total fail. Why does that happen? Why do you get that weird sort of negative image sort of looking effect?
Because all the white pixels correspond to one color.
That's right. Okay, I mean, think about it. These are just some string of bits here, right, that represents this block of white bits. Everywhere that string of bits that represents a block of white bits shows up, it encrypts to the same thing. It doesn't encrypt to white, doesn't encrypt to black, it encrypts to some gray sort of stripy thing, but it's the same. Okay? It's the same everywhere. And everywhere you have a solid chunk of 64 bits of black pixels, they encrypt to the same thing. Okay, and that's enough to give away actually a lot of information as to what the underlying plain text can be, and this image just sort of illustrates that in the most, sort of most obvious way. So remember this picture embedded in your brain. Okay, ECB mode bad. Do not use ECB mode. Okay, because of this picture. And every once in a while, somebody rediscovers this. Like I saw some company, some cryptographic company in Germany or something, and they were saying, "Oh my God, don't use ECB mode. Oh, it's terrible." And they had some pictures like this. So that's been known forever. Okay, so how can we get around that issue? Well, the problem there is that the same plain text block encrypts to the same ciphertext block. We want to avoid that. We don't want the same plain text to show up as the same ciphertext. Well, how did we do that with a classic codebook cipher? We had an additive, right? Remember the additive sequence, another book of sort of random numbers, random looking numbers. You encrypt the message by looking it up in the code book, but then you add the additive to it. If you're at a different place in the additive sequence, same plain text does not look the same in ciphertext, okay, because the additive was different. So that's the idea here. It's not exactly the same, but it's very similar. It's that concept. Okay, we're trying to make same plain text blocks look different in ciphertext. Okay, and so this cipher block chaining is the way to go, or is a way to accomplish that. Now, for this particular mode, we need an initialization vector, an IV, which is the same size as a block of plain text or ciphertext, and it sort of plays the role of ciphertext, so it's not secret. Alice will just generate the IV, she will use it, she'll send it to Bob, so Bob knows what the IV is. It's kind of like the additive. The additive, you would tell the other guy where to go in the additive book to start this sequence, right? So we send that along with the message so they can get the whole process started. Okay, so here's the process. Just like before, we have a plain text message, right? P0, P1, and all that. And we share a key between Alice and Bob. So to start with, the first block, Alice takes the IV, XORs it with the plain text block, and then encrypts it with the key K. She takes this result of that ciphertext, XORs it with the next plain text block, and encrypts that with the key K. She takes the result of that, XORs it. Okay, you got the process here? That's the chaining. You're chaining these blocks together, using the ciphertext to sort of disguise the plain text before you encrypt. So the same plain text block, if this plain text block's the same as this, they're probably not going to encrypt to the same thing, almost certainly not. Okay, because you do this XOR thing first. Okay, so that's encryption. Can we decrypt? And you have to be able to decrypt or people don't like your cipher very much. Okay, so let's see, can we decrypt here? If we know the key K. Well, okay, what does Bob have to do when he receives this? Well, he has to know the IV, so you need to send that to him. So he has to have the IV. So he gets the IV. He takes the first block and decrypts it with the key K. What does he get? When you decrypt, you just undo, right? So you get what's in here. You get IV XORed with P0. If you XOR in the IV, what happens to the IVs? When you XOR something with itself, what happens? You get 0. It just goes away. That's the magic of the XOR. We've seen this a couple times already, right? That's what the one-time pad depends on, that property. That's how it encrypts. Okay, so when we XOR the IV again into this decryption, the IV XOR with IV just goes away, and you're just left with P0. Same deal here. You decrypt this, you get C0 plus P1 XORed with P1. You XOR in C0, which everybody knows, you get back P1. Just keep going. Okay, so you can encrypt, you can decrypt. It works. All right. Okay, so what about CBC mode? This is good because identical plain text blocks do not yield identical ciphertext. That's what we want to avoid, okay? That's the bad thing about ECB mode. But there's a potential issue here, right? I mean, think about, what do you do with the ciphertext? Okay, Alice generates the ciphertext and then she sends it to Bob, right? Okay, typically that's what we're doing here. Well, what happens when you send stuff to somebody else? Well, bad things can happen. One bad thing is that there could just be errors, right? I mean, you get errors in transmission, right? That happens all the time. So suppose one of these ciphertext blocks that you receive is in error. And then you just go through the process and try to decrypt. Well, I mean, suppose this ciphertext block is in error. What happens when you decrypt? Well, you get something that's not this, right? And then you XOR something to it, you don't get C1, right? And then, oh, this C1 was in error. You get down here, it's used again. So you get another block that's in error. So does that mean if I get like 1 bit error when I'm transmitting, it just propagates and all my blocks are messed up? That would be really bad. Okay, that would be impractical. You couldn't really use it. So let's think about that. So what about errors in transmission? Let's suppose that ciphertext block C1 is garbled. It's something else. It's not C1, all right? That's what Bob receives. He doesn't know, so he works with it and puts it into the process. And C0 would be okay because we're assuming the IV and all that was fine. So C0 is okay. But when he decrypts, he doesn't get P1 here. When he decrypts the next one, he doesn't get P2 either. But then, magically, the rest of them are okay, all right? Because why? Because this C0 or C1, I guess, is only used in 2 consecutive blocks. It's not used in any of the subsequent blocks or any of the blocks that come before. So that means, it's not great because it does mean even if there's 1 bit in error in this block, you have 2 entire blocks here that are messed up. So it sort of expands the error, but it doesn't go on forever. Okay, it washes out after a couple of blocks, all right? Okay. Think about it, formula only uses 2 consecutive blocks, okay? So, or only uses that ciphertext block twice, okay? Then it no longer used, okay? So you're okay as long as everything else is okay. Okay, got that? It washes out, okay? Okay, that's important, okay? So we sort of automatically recover from those types of errors. That's good. So that cut and paste thing we looked at is still sort of possible, but it's a little more complex, so we won't show it here. That's, again, an integrity issue, not really a confidentiality issue. Now, if we encrypt, again, this same image, but using CBC mode, and I use the T cipher, okay, same process as before, just change the mode. Hey, this is ciphertext. This is what we want our ciphertext to look like. Bob or Trudy sees this, she has no idea what the original message was, all right? Okay, so got that. CBC mode takes care of that problem. Why does it do this, whereas ECB mode didn't? Because same plain text is not the same ciphertext, okay? All these white blocks here, they encrypted different things. That's why you get this random looking image. Okay? All right, so that's ECB mode, CBC mode. Okay, counter mode, this CTR mode, this is a way that we can use a block cipher like a stream cipher. Okay, what do you do with a stream cipher? You generate a key stream, and then what do you do with that key stream? What's the magic word here? XOR. How many times we say XOR? Okay, so you XOR it with the plain text to get the ciphertext. You generate that same key stream, XOR it with the ciphertext to get back the plain text. And that all works because you XOR the same thing twice, it just goes away. Okay, so we can do that. We can actually do that with a block cipher. We again need an IV initialization vector for this mode. And we will just use the encryption mode, apply it to that IV. It generates a block of bits. And I will use that like a key stream. I will XOR that with block P0. They're same size, so it makes sense. And then I just increment it for the next block, and I encrypt that and XOR that to get the next block of ciphertext, and so on. Now I claim the decryption here. If I have this ciphertext, right, and I want to decrypt, I would, oh, this should be a D here, right, for decrypt instead of E. What do you think? I mean, I've been using these slides for a long time. It's not very likely there's going to be an error in the slides. You have to generate the same key stream, right? So whatever you put here to encrypt, you have to use the same key stream. Okay, so it is an E here. We are just using the block cipher to generate a key stream. Okay, don't think of it as encryption or decryption. It's just to generate random looking bits that I can XOR to encrypt by the same process you use with a one-time pad. Excuse me. Okay, so it is E here. Okay, so I just end up XORing E, this thing twice, and I get back the plain text. That's what's happening here, right? Because the ciphertext looks like that. XOR this, it goes away. And you just get back the plain text. All right. Excuse me. Okay, so this mode, this mode is popular for so-called random access. What do I mean by random access? Just means that suppose you encrypt a file, right? And you want to just jump to some random point in the middle of the file and decrypt that block. Okay, this is a good mode for doing that. Why? Because all I need to know is the IV, the key, and which block I'm looking at, right? And then I just do this encrypt like this, and I apply that to that particular ciphertext block, or XOR it with that particular ciphertext block, and I get back that plain text block. Okay, so it's very good for jumping around different locations in the file. I don't need to decrypt the entire file. I just decrypt this specific block or blocks that I'm interested in. What about CBC mode? Could you use CBC mode for random access? Okay, suppose the file's encrypted in CBC mode, right? Now I want to decrypt one specific block. What do I need to know in order to decrypt that one specific block? I need to know the current ciphertext block and the previous one, right? Because that gets XOR'd in there. But that's probably okay. I probably can get 2 consecutive blocks, so I can use CBC mode for random access. What's the advantage? Then why do we even have this mode?
You only need one block.
That's true, you only need 1 block, but that's kind of a minor thing. I can get 2 blocks, I can deal with that.
You only need one IV? Like a fixed IV?
You only have 1 IV in CBC mode as well. Yeah.
If there's an error in one of the ciphertexts, it's only 1 block wide instead of multiple.
That's another potential minor advantage. There's a big advantage. I don't want to say exactly what it is because it's a homework question and I want you to think about it, okay? But think about it. Okay, there is a reason that this has a significant advantage, okay, over CBC mode for random access. Okay, think about what that might be. Okay, integrity. So everything we've done so far deals with confidentiality, right? We're trying to protect the bits. We're trying to prevent Trudy from reading those bits. You know, no unauthorized reading of the data. What is integrity? What's our definition of integrity?
Detecting when something's changed.
We want to detect unauthorized writing, right? We want to be able to detect it when somebody changes the data, all right? Now, we're going to ultimately have 3 different techniques that we use for integrity. The first one here is CBC mode. Essentially, it's just CBC mode. So learn CBC mode, you get a 2-for, right? 2 for 1. You'll know how to protect the confidentiality, and it's also an integrity check, all right? Okay, so again, it's detect unauthorized writing. So we don't want someone to change the data and we don't know about it, right? It would be great if we could, if we could prevent it, but detection is really the best we can hope for. And the example I gave, I think at the start, suppose, the Federal Reserve Bank of New York transfers $10 billion to the Federal Reserve Bank of Chicago. you know, it's public information that that's happening or that happened, but and so, you know, confidentiality might be nice, but it's not critical. But integrity is super critical, right? If you drop a 0 or add a 0, you know, it's going to be a very costly mistake. Okay, so all that encryption stuff we talked about so far is all confidentiality. You should realize that confidentiality alone does not protect integrity. We saw that with the ECB cut and paste thing, right? We also saw this with the one-time pad, right? Just because someone changes some of the bits, you wouldn't know, right? The process still works. You get a message that seems to make sense, but it's not correct. All right, so we need something else, something in addition to encryption to protect the integrity. Okay, so our first integrity protection scheme is known as a MAC. Okay, MAC is an overloaded term. It's not this kind of computer. Okay, it's, you know, it's a in this case, a message authentication code. I think we might have one other use for MAC. Anyway, so MAC, here we mean message authentication code. It's going to be an integrity check. Essentially, it's going to be a checksum. Okay, we send this checksum of bits, and we can verify that checksum to make sure our data is correct, or as was sent. Now, we're going to do this, in this case, using a so-called CBC residue. So we compute the CBC encryption, and we just save the very last block as a checksum. Okay, we throw away all the rest because for now, we're not concerned with confidentiality at all. We're going to send plain text. Okay, got that? We're just concerned with integrity. Forget about confidentiality for a minute. It's just integrity. We just want to protect the integrity of our message. We're not going to do confidentiality. Okay, so no encryption. Okay, we're just sending plain text. We want to make sure what's received is what was sent. Okay, so we can verify that. Okay, so CBC encryption. Well, when I do CBC encryption, what do I need?
An IV.
I need an IV, and I also need key. Alice and Bob have to share a key. So there's no free lunch here, right? We assume Alice and Bob have shared a key, however they do that, and we'll also need to generate an IV. Okay, so let's suppose we have a bunch of blocks of plain text. Again, we're not trying to protect the confidentiality. We're going to just send the plain text, right? Okay, so we're going to do this process that we do with CBC mode encryption. Same process. We encrypt, you know, we take the IV, we generate an IV, XOR with the first plain text block, encrypt with the key K that we've shared in advance, and just go through that process. When you get to the very last block, we'll call that the MAC. Then what is sent from Alice to Bob is the IV. Bob has to know the IV to get the process started. You send the plain text blocks, and you send the MAC. Okay, so sort of two extra blocks, the IV and the MAC, along with the plain text. Okay, what does Bob do when he receives this? What's he going to do to verify that everything's correct? He's going to do the same thing. So he's going to put this into a CBC mode process, right, into that CBC mode encryption because he has the same key. Now he has the IV. He runs through this process. And if everything's the same as what was used up here, he's going to get the same MAC, obviously, right? If everything's the same, you get the same MAC. The MAC that you compute is the same as the MAC you receive, and you say, okay, the integrity is good. All right, so that's the integrity check, but does it work? Okay, that's the process, but does it actually work? Okay, so let's think about this. Let's suppose Alice has 4 plain text blocks here. She generates an IV, right? Alice and Bob share a key. So she goes through that CBC process. So she generates C0, she generates C1, generates C2, C3, and she calls that the MAC. And what's she going to send to Bob? What do we send to Bob? Send the IV. He has to have the IV. He already knows the key. Don't send the key. We don't want True to get that. What else? No, we're not doing ciphertext. Just send the plain text. Send the IV, P0, P1, P2, P3, and the MAC. Okay, the MAC is serving as the checksum here. Okay, so that's what Alice sends to Bob. IV, P0, P1, P2, P3, MAC. And Bob is going to do the same process on what he receives. If nothing changes, he's going to get the same result, right? Okay, so if nothing changes, it works. but does it detect a change, okay, if something changes? Well, let's suppose Trudy changes, let's just say P1 to something else, call it X. Okay, so there's some tampering. It could just be an error, or Trudy's tampering, so something changed, all right? Now what happens when you run this process? Well, Bob, he has the IV, right? He has the plain text block P0, and he knows the keys. That still comes out the same as what was up here. But when he gets to block P1, it's incorrect, right? So when he XORs it with C0, which was correct, encrypts that with the key K, he gets something else. Let's call it red C1. What happens next? Well, this goes into the process, right? In the next step. And so that next one's almost surely incorrect, and he uses that in the next step. That's almost surely incorrect. And so the MAC he computes at the last step here is almost certainly wrong. And so he says, okay, something's wrong with the integrity of this message. I know it's not what was sent or what was used by Alice when she computed the MAC. Yeah.
Is this the last word problem?
The last word problem?
Word problem?
Could be. Yeah. So any questions on that? Okay, well, think about what's happening here, right? So this says this is just CBC mode encryption, right? It's the same process we use with CBC mode encryption, right? So what this says is when you do CBC mode encryption, if you get an error somewhere in the process, what happens? It keeps going, right? It propagates all the way into the last block, into the MAC. How about when we did CBC mode decryption and you had an error? It washes out, right? It does not propagate. If it propagated, that'd be really bad. We couldn't use it as an encryption mode. So that's beautiful, right? It does exactly what we want. It does the right thing in encryption mode in that errors wash out. It does the right thing in, decryption mode, the errors wash out. It does the right thing in encryption mode, the errors propagate, so we can use it as a integrity check. All right, so it's going to serve dual purposes for us. All right. Okay, so you need to know that. Okay, again, CBC mode encryption. I can just guarantee you it's going to be on the test in some form or another, either as a MAC or as CBC mode encryption or both. Okay, so if you don't have the key, and you're Trudy, you're trying to make changes here. I don't know, what would you do? You would change something, and then you have to change the MAC to match, right? And you don't have the key, so you can't know what that MAC is supposed to be, so, you're hosed. And that's good. That's what we like. Okay, but what about both? Suppose we want both confidentiality and integrity. Well, we're already doing this CBC mode encryption, right, to get the MAC. So why not just do CBC mode encryption and then send the MAC? What's the MAC? It's the last block, right? So let's do CBC mode encryption and let's send the last block twice, and then we get a free lunch. We get both integrity and confidentiality. I mean, that can't work, okay? There's no free lunch in this class, all right? So, okay, so you can't do that. You can't just do CBC mode encryption and get both confidentiality and integrity, and you can think about why that's the case. You have to do two separate processes. You can encrypt, and then you can do an integrity check, and you need to use different keys for those processes. They can be related to each other, but they need to be different keys, all right? Can't just use the same key. Well, that's twice as much work, right? I mean, if I'm going to do CBC mode encryption, then I'm going to have to compute a MAC. I mean, it's like twice as much work. I don't want to do more work than I have to. And so this is actually a research problem, and I think the state of the art is you can do something like the equivalent of about 1.5 encryptions to get both confidentiality and integrity. But for our purposes, just remember they're two separate processes. So you have to do the encryption and confidentiality stuff separate from the integrity check or the MAC process. Okay, quantum computing, my favorite topic. I just want to say a little bit about quantum computers. We'll have a little bit more to say about these when we get to public key cryptography, because it's a little more interesting there. Okay, but quantum computers, I think I gave you an article in the assignment. Yeah, okay, so read that article. It's a little bit skeptical, but I asked you also to look for something that's more positive. IBM probably has all kinds of propaganda on this, so because they're kind of leading the charge here. So I'm sure you can find some more positive spin on this. But quantum computers are designed based on, properties of quantum mechanics, okay, which is a very weird topic if you've ever taken a physics class, right? So quantum bits or qubits, sometimes they're said to be both 0 and 1. That's not quite true. They're actually continuous values. Okay, so each quantum qubit consists of 2 different continuous values. Okay, and so these quantum amplitudes can take on infinite number of values, right? Because they're continuous values. I mean, put it in a computer, it's still finite, but it's a huge number of values compared to ordinary bits, which can only be 0 or 1. So the number of possible states is huge. I mean, it's vast compared to what you could get with similar number of bits on a classic computer. Okay, so there's some potential here for really fantastic computing sort of results. You can just have a huge number of states, but there's all these weird properties of quantum mechanics. Okay, if you observe, and the state collapses and you lose everything, all kinds of weirdnesses like that. So anyway, you have these 2 to the n quantum amplitudes, which give you a huge number of possible states. All right, so there's some potential to do a lot of very powerful computing with relatively small numbers of qubits. But building these computers is really, really challenging. I mean, it's a huge, very challenging engineering problem. And the algorithms that are used in quantum computing are themselves very challenging. Okay, you have to use so-called reversible logic. Okay, so you can't use logic that only goes one way. You have to be able to reverse it. And that really limits the operations that you can do. So the algorithms become very tricky. Okay, so not just the hardware, but the algorithms themselves are harder to come up with. And today, number of qubits in machines is pretty small. I think when I wrote this originally, it was 433. IBM has one with 1121. I just read this morning somebody claims to have about 1,200 qubits in their computer, but there's some debate as to how stable they are compared to the IBM one. So, they're kind of running into the wall already with 1,200 qubits. You need a lot more than 1,200 to do things really interesting. But anyway, we'll see. We'll see how this works out. But it's certainly a very big engineering challenge. Okay, but from the symmetric cipher point of view, what's interesting here is what about the algorithms? Okay, people, have looked at quantum computing. I actually have a master's student working on a quantum computing related project now, sort of malware detection using quantum computers. What could you do in that case? And so you have to think about what kind of algorithms could you come up with. And you can actually test algorithms, right? There's simulators for quantum computers of any size, and so you can test various algorithms that you come up with. And so the best algorithm that would have an effect on symmetric ciphers is known as Grover's algorithm. It's designed by that guy on Sesame Street, Grover. Okay, Lou Grover. Okay, this guy designed this algorithm, and it does speed up the attack on symmetric ciphers. Okay, it's about a square root factor. Okay, so it's a square root factor speed up compared to an exhaustive search on a symmetric cipher. So what that means is, if you had a symmetric cipher that had a key that was in bits, okay, using a classic computer, a classical machine, where you have to do an exhaustive search, the work factor would be about 2 to the n minus 1, right? We try about half the keys, and then we get the correct answer. All right, so a secure cipher, this is your attack on a classic computer. On using Grover's algorithm on a quantum computer, it's about 2 to the n over 2. That's the square root of 2 to the n, okay, 2 to the n over 2. So that's a very significant speed up. But as a practical matter, what does that mean? It means if we just double the key length, right? So if we just take a cipher, say we're using AES with a 128-bit key, which is very popular today, if quantum computers come into being and they're powerful enough and have enough qubits and all that, all I would have to do is double the key length. And I could use AES with a 256-bit key, and it would take just as long to break that on a quantum computer as it takes to break a 128-bit key on a classical machine. Okay, so I mean, it does slow things down a little bit using longer keys. You have more rounds in AES and all that sort of stuff. So it's a little bit slower, but it's not earth-shaking. Okay, it doesn't destroy the whole encryption thing, right? We can still encrypt using symmetric ciphers. Okay, so it's certainly not devastating against symmetric ciphers, all right? Even if these things come into being and they do exactly what they're supposed to do with unlimited number of qubits and so on, all right? We'll see the story's a little different when we get to public key cryptography. Okay, there it really does make a difference, all right? Okay, everybody got the point here? Okay, quantum computing, not the end of the world for symmetric ciphers. Oh, yeah, I did want to say a little more here. Okay, yeah, I just want to finish up this chapter just a little to summarize. So we have talked about confidentiality and integrity, and we can do both of those things with symmetric ciphers. Almost everything we talked about dealt with confidentiality. We've only got the MAC for integrity, but integrity is important. Okay, don't think it's less important. And confidentiality kind of comes in two flavors. One, we typically have talked about it in the sense that you encrypt the data and then you want to transmit it. You know, Alice encrypts it, sends it to Bob. But you can also think about encrypting the data on your hard drive, right? It's a little different scenario, but you know, same sort of techniques work, all right? For integrity, we have MACs. We'll see that these ciphers come up again when we talk about authentication protocols, which is a big deal later in the semester. And from a conceptual level, you can do anything you can do with these, you can do with hash functions and vice versa. But it's still useful to have separate actual algorithms to do these things.